Welcome to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim Research and Development Manager, and I'll be serving as the moderator for the webinar today. I'm pleased to welcome today's presenter, Zach Lerner, who is joining us from Colorado State University. Ray Browning, Zach's advisor from the Physical Activity Lab at CSU, is also joining us. So OpenSim is a freely available software application for visualizing musculoskeletal structures and simulating movements of humans and animals and more. The application includes tools for general purpose inverse dynamics, optimization to estimate muscle and joint forces, methods to create simulations for motion capture, and then tools to analyze and visualize the result of those simulations. The first goal of our webinar series is to showcase cutting-edge research that's being performed with OpenSim. OpenSim is also a growing and geographically diverse community of users. So the second goal of our webinar series is to provide an easy platform for the OpenSim community to communicate and collaborate. Before we get started, I have a few reminders about the webinar format. Questions will be addressed at the end of the presentation using the Q&A panel. If you need any additional technical help during the webinar, you can consult the guide on our website or send a private chat to the host or to me. Now I'd like to introduce Zach Lerner. He's a doctoral student in the School of Biomedical Engineering at Colorado State University. Zach is quickly becoming an expert and big contributor to the OpenSim community with webinars like this, by participating in our workshops, and sharing his work on SimTK. Researchers like Zach enhance the community now and will keep it running in the future. Today he'll be describing his work studying walking biomechanics in the obese population. In this process, he's compiled lots of troubleshooting tricks and tips that will help out all users. So with that, I'll let Zach take over with his presentation.
Okay, thank you, Jen. Hi everyone, my name is Zach, and I'm really excited to be giving this webinar talk. Today I'll be discussing some OpenSim basics, and I'll be using our analysis of the locomotion biomechanics of obese adults to highlight the functionality of utilizing OpenSim to run musculoskeletal simulations. To give you a little background, I'm a graduate student in Dr. Ray Browning's Physical Activity, Energetics, and Mechanics Lab at Colorado State University. We're interested in analyzing the effects of obesity on gait kinematics and kinetics in order to identify possible mechanisms of musculoskeletal injury, for example, osteoarthritis. Our overall objective is to better and more safely prescribe exercise as a form of weight management. Specifically related to OpenSim, I'm interested in improving our confidence of modeling obese individuals by incorporating obese-specific model parameters. I would now like to provide you with a motivating example of why we felt it necessary to make a research-specific musculoskeletal pipeline when studying the obese population. One of our research goals is to determine kinematic differences between obese and normal weight individuals so that we can make inferences about any adaptations that we observe. If we analyze the joint kinematics using a rudimentary data collection procedure and a generic musculoskeletal model, we see a completely different result compared to a simulation with research-specific improvements. The figure here on the left compares the hip abduction angle, while the figure on the right compares the hip flexion angle of the same subject for the same gait cycle between the two processes. Clearly, these results would tell two completely different stories based solely on whether or not research-specific improvements were made. I would now like to express the goals of this talk. The first goal is to convey the importance of collecting meaningful experimental data. The second goal is to demonstrate a need for creating research-specific protocols. And the third goal is to provide useful tips for analyzing large-scale research studies. And just as a quick reminder, I expect the audience has a basic understanding of OpenSim workflow. So this means having some knowledge of scaling an OpenSim model or running residual reduction algorithm. Additionally, it will be beneficial to be aware of the principles used in resolving muscle forces from net muscle moments via static optimization or computed muscle control. At this point, I would like to take the time to learn what research topics the audience is interested in by taking a quick poll. You should see a question dialog box popping up on your screen momentarily. Please select the box related to your research interest. While we're waiting for the results to come in, I would like to encourage anyone that has specific questions pertaining to their own work in OpenSim to create a post on the OpenSim users forum. It's a great way to get feedback on problems that you may encounter, or to gain information on standard methodologies. I myself find it very useful, and people are usually quick to respond. All right, so the results are in, and like I anticipated, a few of you are interested in using OpenSim to analyze pathological gait, as well as amputee gait. It's great to see what topics the audience is interested in researching, so thank you for the input. And now that I have an idea of what you're all interested in, I'll now be able to better customize this talk to incorporate relevant items. We use OpenSim to answer a number of our own research hypotheses. Like I mentioned before, we analyze gait kinematics in order to quantify the effect of obesity on energetics and musculoskeletal injury and pathology. We'd like to know if obese walk a certain way in order to reduce metabolic rate, or if gait differences are a result of relative muscle weakness. We also use OpenSim to estimate the effect of obesity and walking speed and grade on tibiofemoral joint contact forces. And finally, we're working on utilizing information from OpenSim's computed muscle control analysis, specifically the muscle states, to better understand the effect of obesity on muscle mechanical energy expenditure. We can use this information to design and gauge effective interventions that maximize energy expenditure while simultaneously minimizing the risk for injury. On this slide, our OpenSim workflow is visualized in this flowchart. In green, I've highlighted the research-specific goals mentioned on the previous slide. The red arrows represent the location of the research-specific improvements that will be discussed in this webinar. Moving down from data collection, we incorporate subject-specific data into a musculoskeletal model. The model is then scaled, and inverse kinematics is used to generate the body segment motion in the model from the experimental markers of the subject. Next, we run the residual reduction algorithm to minimize the effects of experimental error. It works by modifying the torso or pelvis center of mass location and allowing the kinematics to vary slightly so that the motion of the model is dynamically consistent with the ground reaction forces. Whether we use static optimization or computed muscle control to resolve the individual muscle forces from inverse dynamics depends on the application. In short, we use static optimization instead of computed muscle control to provide the muscle forces used as inputs into the joint reaction analysis, because they provide the most realistic and repeatable results. And additionally, this seems to be the convention within the OpenSim community. On the other hand, we use computed muscle control when we want to constrain the activation to match experimental EMG. This is something that cannot be done in static optimization. We also use CMC if we need the detailed information on the muscle states, for example, in our study of muscle energetics. The order of this presentation will follow that of our webinar goals. First, I'll talk about how to effectively prepare your data for importing into OpenSim. I'll then use my own research to provide examples of how you can create a more accurate research-specific simulation. This will incorporate creating a custom marker set, updating model parameters, and using EMG data as inputs into control constraints. Finally, I'll present a teaser of our recent results where we utilize the joint reaction analysis to estimate bone-on-bone contact forces in obese individuals. Now that we've discussed our motivation for using musculoskeletal modeling to answer our research questions, I'll now talk about incorporating experimental data into OpenSim. To give you a point of reference of where we are in the workflow, we're located here at the highlighted red arrow. This may arguably be the most vital step in this entire workflow, because without it, you can't use OpenSim with your own data. The basic protocol for importing experimental data into OpenSim is visualized here at the top of the slide. First, kinematic and kinetic data is collected using a motion capture system. Next, the synchronized data is exported as a C3D file. And the final step is to extract the properly formatted marker trajectory data and force plate data using Matlab and a gate extract toolbox. A gate extract toolbox is essentially a Matlab script that is created to extract the kinematic and kinetic data from the commonly used C3D file format and reformat them into something that can be used in OpenSim. There are a number of gate extract toolboxes available on various SimTK project pages, and I believe Tim Dorn has created one that is widely used. While most of these files allow and require you to customize the code, I would suggest finding a toolbox that is as close as possible to your own lab. Or rather what I mean is to find a toolbox that has a similar lab setup as to your own. For example, if you have an instrumented treadmill like we do, seek out a toolbox that has a similar initial setup. Some modifications may be required and may have to do with aligning the coordinate system of your laboratory with that of the toolbox, which then transforms the data into OpenSim's coordinate system. Once set up properly, the gate extract toolbox will automatically format the data for use in OpenSim. The marker trajectory data, for example, should be in .trc or track row column format, while the force plate data should be in the .mot or motion format. It's important to ensure that the marker names and forces are labeled consistently. Otherwise, there will be errors when associating the data to the model. Down here on the right, I've made a visual representation of our lab's origin, the origin of our force plate, and the origin of the coordinate system used in OpenSim. This should give you a better understanding of why we need to make certain rotations and translations to the reference frame used in experimental data collection, and why every setup is unique. You can see that the OpenSim coordinate system defines the upward direction as the positive y, while in our lab, positive y is in the forward direction. If you're having trouble aligning your data for use in OpenSim, I would suggest creating a graphic similar to this for your own lab. The preview motion data feature in OpenSim can also be useful for understanding the rotations required to align your kinematic and kinetic data. I'll demonstrate this now. So what I'm going to do is I'm going to reopen up this file. So I'm in OpenSim 3.0 right here. And I'm going to select Preview Motion Data from the File menu. First, I'm going to open up the marker trajectory data. And next, I'm going to open up the ground reaction force data. What I can do is I can select both of these files, and I can sync the motions. This allows me to see if the force plate or the ground reaction forces align with the motion of the markers. And clearly we can see that a transformation is needed to align these forces with that of the model or that of the markers. So what I can do is I can right-click and hit Transform. This allows me to apply transformations or rotations specifically to that ground reaction force vector. So what I can do is I can rotate that in 90 degrees, negative 90 degrees, and it looks like that's going to align the forces with that of the model. Additionally, you can save this file so that when you run additional analyses, that transformation remains reflected in that file. But I don't need to do that, so I'm going to hit Cancel. I'll close these out. So you can use this tool to understand the transformations that need to be made when using a gate extract toolbox, so it's very handy. After your experimental data has been properly imported into OpenSim, it may be useful to assess its quality and accuracy. This can be done very easily by visualizing the data using the plotting tool. For example, the center of pressure location can be plotted alongside the location of the medial metal ankle markers to analyze the point of force application on the foot. What I mean by this is that if you want to check that the translations and rotations that the gate extract toolbox applied to the data was done correctly, you use the plotting tool to see if the center of pressure or the point of force application on the foot, which is this green arrow here, to see if it's within the bounds of the medial and lateral ankle markers, so here and here. If the center of pressure is outside of this footprint, then you can conclude that there was some error in the translations that was applied to the kinematic or kinetic data. This error would likely cause a dynamic inconsistency and may cause an analysis to fail. So if you have experience working with OpenSim, then you'll know that there are some instances in the gait cycle when simulations seem to fail for no reason. One such instance is a heel strike. And the reason that simulations tend to fail here is because large accelerations are likely, and the filtered ground reaction force data may be problematic for static optimization or computed muscle control. At the instant of heel strike, the unfiltered ground reaction force data will fluctuate around 0, so it may look like this. It's common to see the filtered data go slightly below 0 right before heel strike. While it may not cause the simulation to fail, it may require more residual or non-physical forces to get it to run. So if you notice a spike in the use of residuals at certain gait events, it's a good idea to plot the force data at that instant in time. You can see how it may be difficult for the optimizer to solve the muscle forces to account for a negative or tensile force at the foot. In this example, one solution may be to expand the integration time window so that it's wide enough to pass over this negative period. So that would be a window greater than this distance here. Or another solution would be to simply set these negative forces to 0. Now that we're a bit more comfortable with getting the raw data into OpenSim, I'll now talk about the ways in which you can customize your simulation to account for your particular research topic by highlighting some of the methods we've used to more accurately represent obese individuals. As a point of reference, I'll now be talking about improving data collection, seen again on this familiar flowchart as the red arrow. We realized early on that a conventional marker set placed on the peripheral adipose tissue yielded highly inaccurate results. Essentially, by using the convention, we are using garbage data and getting garbage results. On the next slide, we'll look at another motivating example. This time we'll compare muscle force output and joint reaction results between a generic model and our obese-specific model. Given the same subject and gait cycle, we'll see two very different results. This highlights the fact that just because the simulation runs, it doesn't mean that the results are accurate. Now let's take a look at this other motivating example. Another of our research goals is to determine how muscle forces change with obesity. Ultimately, we're interested in determining potential mechanisms for the initiation and progression of osteoarthritis. So naturally, we look to estimate the magnitude of joint contact forces. Again, we have a comparison between the generic and improved upon models. The plot over here on the left is the force output for the rectus femoris muscle, while the plot on the right is the tibiofemoral joint contact force. The muscle force estimates aren't even remotely close to one another, and the joint contact force is pretty different here at that first peak. This time it's fairly obvious to see which line represents the generic model, which is blue, and which line represents our research-specific improvement, which is the red line. To turn our data from garbage to great, we developed a new and improved reflective marker set. The goal of any marker set is to capture the functional joint centers, the segment lengths, and the segment motion of the subject. The set we developed, called the CSU full marker set, has 51 reflective markers, in contrast to the limited or Helen Hayes marker set, which is 22. We found a vast improvement when we utilized digital markers and additional marker placements via clusters. A digital landmark is defined relative to physical bony landmarks of high confidence on the same segment. During the static calibration trial, the landmarks are digitally marked via a digitizing pointer. The relationship established between the digital marker and its defining physical markers are used to determine the location of the digital marker during the motion trial. This should become a little bit more clear on the next slide. There are several instances when placing a digital marker may be beneficial, the most obvious being when a physical landmark is obscured from view. Here we have a side-by-side comparison of our limited marker set and the CSU full marker set. The smaller arrows are pointing to the digital markers on the right iliac crest and ACEs locations. The larger arrows are pointing to the locations of the marker clusters on the thigh and sacrum. This one's on the thigh and this one's on the sacrum. A marker cluster contains a number of markers attached to a rigid fixture. You can see that here and here. The relative, nonlinear positions of the markers remain fixed. This has been shown to improve segment tracking in all three planes. At the bottom of the screen, we have a graphic representing the digitizing pointer. This time it's probing the ACEs location. What happens is that the digitizing pointer will probe and mark a bony landmark during the static calibration trial. That location, so this location here, is then defined relative to other landmarks of high confidence, in this case the sacral cluster. We found a more accurate representation of joint centers, scaling, and inverse kinematic results, and ultimately more accurate net muscle moments and muscle force estimations when using our full marker set. I would like to point out the miraculous weight loss exhibited by one of our subjects after only one trial on our instrumented treadmill, and we call him Mr. Obese. And it's hard for me to gauge feedback from the audience when I can't see you, so I only assume that this joke was a hit. Human bodies and OpenSim models are kinematic and kinetic chains, and so improper identification of joint centers at the hip, knee, or ankle will have a profound and noticeable effect on elsewhere on the body. These videos are of the same subject and the same gait cycle. The only difference is the markers that were used in scaling and inverse kinematics. Looking at the plot of the hip joint angle versus time up here, we see a large difference between the limited and full marker sets. In this case, the difference is about 20 degrees. This is mainly due to an inaccurate anterior shift in the hip joint center in the limited model. The next step in refining a basic musculoskeletal model for the study of obese subjects was to incorporate subject-specific mass and inertial properties into the OpenSim model. Back to our flow chart, we're at this location, pointing to the model. Incorporating custom mass and inertial properties may need to be done when modeling prosthetics, exoskeleton-assistive type devices, or when scaling doesn't accurately represent the mass distribution of the subject. The first step is to take the mass or inertial measurement. For humans and animals, this can be done by collecting DEXA data. For devices being designed using CAD software such as SolidWorks or Pro-E, material properties can be applied to the parts and the mass properties then determined. It's very easy to input the updated mass and inertial properties into a model using OpenSim 3.0. This is because now live model editing is available in the GUI. It's important to understand how the location of the segment center mass is defined. In OpenSim, it's defined with respect to the segment's frame of reference, origin. If there's any doubt to where this may be, its location can be visualized in the GUI. Here you can see a negative displacement in the y direction of the center of mass of the thigh relative to the femur segment's origin. There's a negative displacement along this y-axis, negative 0.17 meters. In contrast, moment of inertial properties are defined relative to the center of mass location, not the segment origin. So they're defined around here. It's possible to run a Matlab script to automatically update a model file based on DEXA or other anthropometric measurements. This would be useful when there are many subjects being analyzed and updating through the GUI becomes tedious. The OpenSim API is now accessible through Matlab, which makes this process simple. After updating the model parameters specific to the obese population, we found improved CMC results. There was less fluctuation in muscle activation, which may not change the story significantly, but it helps to create a more dynamically consistent model. This allows our simulations to run more efficiently. Looking at the figures, the red line represents the obese-specific model parameters, and the blue line represents the generic model parameters. The red arrows are highlighting locations of significant deviation from the improved model. Clearly, these changes don't affect peak force output during gait, which isn't surprising given that the peak muscle forces are usually seen during ipsilateral stance when the motion is minimal. I'm going to now move the discussion towards incorporating EMG data to improve the results of computed muscle control, or CMC. Once again, looking at our simulation flowchart, we're located here down in the bottom right. In OpenSim, we use CMC to resolve joint torques and forces from inverse dynamics into individual muscle forces using an optimization parameter. The important thing about CMC is that you can utilize collected EMG data to constrain the excitation of important muscles during a movement. This will better ensure that the simulation is representative of the movement in question. By constraining a few important muscles, the CMC optimizer will yield an improved solution of the remaining unconstrained muscles. It's possible to establish on-off cut points for the muscle excitation pattern based on the baseline average of the EMG signal and a scalar multiple of the standard deviation, the convention being 3 times the standard deviation. In this figure, I've plotted the filtered EMG data for the biceps femoris and gastrocnemius muscles. So this is clear, this is the gastroc, and this is the biceps femoris. The on-cut points are indicated by the black hash marks, and the off-cut points are indicated by the red hash marks. So this is on, and this is off. This would be our period of on activation. OpenSim has a built-in excitation editor, which allows you to specify minimum, maximum, or specific excitation patterns. These values are stored in an XML control constraints file, which orders the nodes as a function of time. The picture on the left is of the OpenSim control constraints editor, and the screenshot on the right is of the XML file storing the same data so it can be used in CMC. Now with OpenSim 3.0, a new muscle class allows for a minimum activation of 0.01. I've created a Matlab script that converts the raw EMG data into periods of on or off excitation and populates a control constraints file with that information. To populate the control constraints file, we can take advantage of the XML tree structuring. There is some general setup required when using this script. First, the muscles of interest need to be specified. Next, we need to specify periods of baseline activation, which should be based off of observation and published data. Finally, the script will request the user to input the start and end times of the current gait cycle. The raw EMG data should be filtered and normalized in length, in this example, to 1 gait cycle. In OpenSim, we need to identify the start and end times for the desired gait cycle. To do this, we'll identify right heel strike events during the motion trial. So I'm going to demonstrate that now. I'm going to go back into OpenSim, and I'm going to use the plotting tool one more time. I'm going to load the ground reaction force data for a motion trial. I'm going to plot the force in the vertical direction on the first force plate, because that corresponds to the right leg, which is the leg that we have collected EMG data for. I'm going to plot this versus time. You can see that there's approximately 14 or 15 gait cycles, but we want to narrow this down to 1. So I'm going to zoom in on the plot. And we can see that at approximately 4.3 seconds, we have right heel strike. So that'll be our on time, or our start time. And then at around 5.5 seconds, the right heel comes into contact with the force plate again. That's going to be our off time. So now working in Matlab, what we're going to do is we're going to run this EMG to control constraints Matlab script. The first thing that's going to do is it's going to ask us for the EMG data file. We'll select that, and it's a .csv, or a comma-separated value. Now it's asking us to input the start time. So it's 4.3 seconds, and then the end time was 5.5. And this will take a second to run. And now we have this plot of all 6 muscles that were included in the raw or in the EMG data, and you can see the on location signified by the black crosshairs, and the red locations indicate the end of that on signal. So now what I would like to do is open up this updated control constraints file with this appended EMG file name using the OpenSim excitation editor. So under the edit menu, hit excitations, and I'm going to load that file. And I'm going to look at the soleus muscle. Soleus right leg, hit OK. And now we can see that the muscle excitation is constrained, starting at 4.3 seconds to 5.5 seconds. So now we know that it's constrained and it's at the gate cycle that we're interested in. There is a little setup required, but it's pretty basic. And it has to do with naming the muscle files, naming the muscles that were collected with the EMG data. So in our case, we have these 6 muscles. Another step is to specify the actuator names that are in the OpenSim model. So for example, we're going to relate the biceps muscle, which corresponds to the first column of data, to the biceps femoris long head and the biceps femoris short head. And these are the actuator names in the OpenSim model. And that's pretty much it. It's relatively easy. Okay, back to the slide. Here we have visualized all of the muscles from the EMG data in the excitation editor. So I just visualized the soleus, but here are all 6 of them. On this slide, we have a visual representation of the actual EMG signal in black, plotted over the activation results of CMC from the vastus medialis muscle. In red are the CMC results when we incorporated the EMG data using the control constraint file. And in green are the activation results using a non-constraint model. The overlay of the black and red lines aren't perfect, but they are in much better agreement compared to the green generic line. In general, I look to see that the muscle is active around the same time when it's supposed to be active, and off when it's supposed to be off, like around here. And obviously, the more closely the theoretical activation pattern is to the experimental pattern, the better. Here, I have the force estimation for various muscles based on 3 different simulations. The first simulation, plotted in red, is a generic marker set, did not incorporate obese-specific anthropometrics or EMG data. The second simulation, plotted in blue, incorporated the CSU full marker set and obese-specific anthropometrics based on DEXA data. While the third simulation, plotted in green, used the same model, but now it incorporated that EMG data. And the muscles starting from the top left are the gastrocnemius, semimembranosus, soleus, and then finally the biceps femoris. Also plotted are periods of muscle activation based on the experimental EMG data, and these are represented as the solid gray lines. So here for the gastrocnemius, we have activation here, and for the semimembranosus, we have activation at the beginning and end of the gait cycle. The red arrows point to locations of significant deviation from the EMG model in which we have highest confidence. You can see how these green lines match very closely to the periods of experimental muscle activation. The generic model gave us the most fluctuating and abnormal results, while the obese-specific model is in better agreement with the EMG model. Clearly, using the generic model to answer a research hypothesis could lead to an entirely different or inaccurate conclusion compared to the improved research-specific model. And I hope that my EMG Matlab script will allow people to more easily incorporate experimental EMG into their own simulations. And you can see that the effect is rather profound. To conclude the topic of creating research-specific simulations, I hope the results from the previous slide demonstrates that a number of simple and easy modifications can be made to improve our confidence in musculoskeletal modeling. Beyond looking at the end results, there are other ways to evaluate the accuracy of the simulation. Residual forces from residual reduction algorithm, or RRA, can be used to identify a more dynamically consistent simulation. On the left graphic of this slide, the residual forces in the x direction are plotted for the generic model in red and the modified model in blue. On the right are the residual moments about the z-axis. These plots are both after one iteration of RRA. And based on these results, I would say that the research-specific model was more dynamically consistent because it required lower non-physical forces to run. OpenSim gives you all the tools that you may need to customize the simulation, so I would recommend taking advantage of them. The typical OpenSim workflow begins with scaling and inverse kinematics, moves on to RRA and static optimization, or CMC, and it finally ends at some analysis. This workflow can be iterative and time-consuming. For research studies with a large number of subjects, it may be useful to create a batch processing script. With OpenSim 3.0, the OpenSim team is rolling out a number of really amazing features that will allow the API to be accessible through Matlab. It's now easier to run analyses, update model parameters, and populate fields within settings files. If designed correctly, a batch processing script can reduce user error and ensure that all subjects are processed in an identical fashion. In simulations where consistency matters, this may allow for more accurate comparison between groups. I've created a number of scripts in Matlab which can help to save time when analyzing many subjects. For example, one script populates all of the required fields in the settings files for a given subject and trial, and another runs each OpenSim process sequentially using the GUI and updating the settings file simultaneously along the way. And I'm going to make these files available on our project page. I'll conclude this talk by presenting a few sample results from our analysis of obese locomotion biomechanics. In order to evaluate whether slow uphill walking would be a safer form of exercise in the obese compared to fast level walking, we used OpenSim to estimate the tibiofemoral joint contact forces at a number of speeds and grades. We found a reduction in the first peak of these bone-on-bone forces during slow uphill walking, but no change in metabolic output. So we're looking here at this first peak. We conclude that slow uphill walking may be a way to reduce early stance knee joint loading in obese adults while maintaining aerobic intensity. This can be explained from reduced ground reaction forces during walking at a slower speed and the alignment of the ground reaction force vector relative to the knee joint center. After the completion of this webinar, I will be posting a sample of our experimental data on our project page, along with the example Matlab codes that are used for batch processing and incorporating EMG data. The OpenSim team has done an excellent job creating a detailed user's guide, which I recommend as the first stop for troubleshooting your own simulation. If you know how the simulation works, then you understand why they fail. I would really like to thank everyone for tuning in, and I hope you found this webinar useful. Our lab is extremely grateful for the support we've received from the entire OpenSim team. Specifically, I'd like to thank Edith Arnold for making her own work on batch processing public, and Matt Demers for letting us use his model and for his general assistance. And for my own team, I'd like to acknowledge the work from Wayne Board and Derek Hates. Much of this work in the presentation was from them, so thank you guys. And thanks again, and now I'm going to give control back over to Jen.
All right, thank you, Zach. That was a great talk. Now let's start the Q&A session. So as I mentioned at the beginning of the webinar, all the questions will be text-based using the Q&A panel. So you need to go and find that Q&A panel on a Mac. So the way to find it on a PC is shown here. If you're using a Mac, you hover over the green bar at the top of your screen and go to Options and choose Q&A. Then you can just go ahead and type in your question. Make sure you ask all panelists so we can all see your question. All right, so while we're waiting for the audience questions to come in, I'll go ahead and ask a question. Can you talk a little bit more about how you use markers to define pelvis kinematics and explain a little bit more about why you use the digital markers and why you feel more confident about using the cluster of markers on the sacrum versus actual markers on the anterior pelvis.
Sure. So let me back up and take us to that slide. So to reiterate that question, I think that you're asking me, first of all, why we utilized digital markers, how we utilize them, and how we now have, I think we have better confidence in those results. So a digital landmark can be placed when a physical landmark is obscured from camera view or if it's unable to be accurately denoted because of soft tissue, or additionally if a marker is unable to be placed due to subject comfort level. So what happens is that during the static calibration trial, the landmark is palpated, and then the digitizing pointer, so this thing here, marks the location of the bony landmark. So the pointer makes a depression into the adiposity, and that's captured in a motion trial. Next, in model building, the digital marker locations are then defined relative to these sacral cluster, and this is particular to the pelvis. And the relationship established between the digital marker and its defining physical markers are then used to determine the location of the digital marker during the motion trial. As for how or why we think we have higher confidence, a perfect example would be looking at the results from the residual reduction algorithm. And what we see when we were to run residual reduction algorithm on the generic model, or the generic marker set, so that's the Helen-Hayes model, we would see extremely high residual forces so that the simulation would be dynamically consistent. When we make our improved marker set and we incorporate that into the model and then we run residual reduction algorithm, we see much less residual forces are required to get, or are required for the to get it to run properly. And additionally, we see that there are much less changes to the kinematics. So if you remember in RRA, it changes slightly the kinematics of the model. And when we have our improved marker set, the changes that are made are much less. Does that answer your question?
Yeah, that has me convinced. Great, thanks. Moving on to a question from one of the audience members. So this is a question from Anthony Santago. So you showed using some Matlab code to automatically generate control constraints. Do you have any sample code that creates a states file from scratch? Or if you don't, can you maybe talk about how you might do that?
I don't have code that does that, and I'm actually a little bit confused by the question. So the question was if I have any Matlab code that creates a states file.
Yeah.
And Jen, can you clarify that at all, or?
Well, I think what he's getting at is that, say you don't already have some states from a simulation, how would you go about generating one from scratch? And I think that you could pretty easily set up a script similar to yours, just generating states instead of.
Right. So maybe you have a motion trial, but you didn't collect EMG data, and you'd like to incorporate EMG data from published literature on the important muscles. You could certainly modify the Matlab code that I've written to easily populate that control constraints file based on those the timing from published data.
Mm-hmm. Okay, thanks. Hopefully that answered Anthony's question. It's a little hard since we're reading text. Okay, he said thank you, so I think he's happy.
Okay, he's welcome to email me, and I can discuss privately if he has any more questions.
Okay, great, thanks. I have another question. This one is also about how you constrained your EMG and compared the simulated activations and forces to the EMG from your experiment. So I noticed that the muscles that you show, gastrocnemius and soleus, they matched pretty well without applying any constraints.
Right.
But then the hamstrings muscles, the semimembranosus and the biceps femoris long head, they seem to turn on in the middle of the gait cycle unless you apply those constraints. Do you have any ideas on why the hamstrings versus the plantar flexors needed the constraints?
Right. So the results from this slide are specific to an obese subject that we've been analyzing. And when you analyze an obese subject rather than a normal weight individual, the generic OpenSim model undergoes pretty dramatic scaling. And so it's possible that the scaling of the hamstring muscles aren't ideal, specifically relative to the origin on the pelvis, because again, it's an estimation based off of our digital markers. And so it seems to me like that is one of the main reasons that we have this abnormal force production. And you may not see that abnormal force production in a normal weight individual or with the generic simulation.
Okay. So you don't see that as much? Have you analyzed normal weight individuals?
Right, yeah, and we don't see that quite as much.
Okay, interesting. I'll give people a couple more seconds to ask any final questions. Just one final quick follow-up. So you showed where your SimTK project is. How did you find those other user-contributed gate extract toolboxes?
How did I personally find them?
Yeah.
I went to the OpenSim resources page, and I just used the search field and typed in gate extract toolbox, and a few different results popped up. What's nice about searching on the resources page is you get results from the users forum as well as results directing you to the actual SimTK project page. And it's pretty useful to see others' comments on if they've had any problems with implementing the gate extract toolbox, or it's very useful. So I like to search through that resources page. Great,
yeah, that's what I do too. So we have time for one final question. This is from Bemis Tumanadu. Apologies if I did not pronounce that correctly. He's wondering, did you include the psoas major in your musculoskeletal model? And if you did, whether you recorded any EMG activity of psoas or iliopsoas?
Yeah, so that muscle is it's modeled within the OpenSim model that we use, but it's a very difficult muscle to collect accurate EMG data for, especially in obese individuals. So we weren't able to include that muscle in the current analysis that we've run. But it doesn't mean that you wouldn't be able to customize the Matlab code that I've written to include additional muscles. So it would be no problem if you collected that EMG data for your own subjects, and you could certainly implement that.
Okay. Yeah, you could perhaps use data from the literature, from fine wire EMG or something like that, although in your case, then you would assume that it's the same EMG for normal weight and obese individuals.
Right, right.
Okay, I think we'll go ahead and conclude the Q&A session. If you can bring up those final slides for me, Zach.
Sure.
Thank you all for the great questions that came in. I should definitely point out our sponsors. So the OpenSim project and this webinar series are supported by several grants from the NIH and the EU, including an NIH grant that funds our National Center for Simulation and Rehabilitation Research. We're also funded by the DARPA Warrior Web program. And I also encourage you to visit our website. At our website, you'll find information about future webinars. For example, we'll have another webinar next week with another external speaker, or actually set of speakers. We'll have BJ Fregley and Carolyn Patton talking about modeling-based rehabilitation for patients with stroke. And you'll also find at our website that search box that Zach was talking about and many other resources. So with that, I'll go ahead and close the webinar. Thank you, Zach, and thank you all for participating. You'll see a survey that'll appear in the pop-up window at the conclusion of the webinar. Please fill this out because it'll help us improve future webinars and choose upcoming topics. So thank you again. We hope you'll continue to stay involved with OpenSim.